Hello everyone. So in this lecture, we're going to discuss section 8.3 that's looking at inverse trigonometric functions. So when we talk about the inverse, recall that we use this notation f raised to the negative 1 power. And so for instance, if you have f of x equals sine of x, then f inverse of x is going to be written as sine inverse of x. So for instance, since we have, let's say, sine of pi over 6 is equal to 1/2, then that means pi over 6 equals to sine inverse of 1/2. So recall that for your inverse function, we switch the y's and the x, right? And so we should be familiar with these notations and ideas from when we did inverse. Now, when it comes to the inverse, recall that the functions must be one-to-one. But if we look at the standard graph of sine or cosine, recall that it's periodic. For sine, looks like this, and cosine looks like this. And so notice if you do the vertical line test, not the vertical, the horizontal line test, that the functions may fail. But if we are able to restrict the domain of the functions, then we are able to get them to be one-to-one. Specifically, if we are able to restrict the sine function between negative pi over 2 and pi over 2, then as you can see, it now becomes a one-to-one function and it passes the horizontal line test. Likewise, for the cosine function, if we restrict the function between 0 and pi, you'll see that it also becomes a one-to-one function that passes the horizontal line test. Okay. Tan is naturally a one-to-one function, so we don't have to restrict the domain. Just a little bit of note here, all we need to take away is that we sometimes say arcsine or arcsine of x, representing the sine inverse, or arccosine or arccos of x, representing cosine inverse, or arctangent or arctan of x. Okay. Also recall that when we talk about the domain and range of a function versus its inverse, the domain of the inverse, or the domain of the function, is going to be the range of the inverse, and the range of the function is going to be the domain of the inverse. Recall, because we are switching the y's and the x's. So this is just a quick recollection of what we did before, but it's not being applied to the trig functions. Likewise, when we did the graphs, recall that if we draw the graph of f of x, in this case, let's say we're looking at the sine graph. If you draw the graph of the sine function, if you want to see what the graph of the sine inverse function is, then all you need to do is reflect your function about the line y equals x, and then you will get your graph. Or you can switch your points and plot those and you get your graph. Okay, so like I said, it's just, we're just recalling all that we did before, but we're applying it to trig functions. So there are some properties that are very helpful when we're solving different trig or evaluating different trig expressions. So for instance, if we have angles that are in the interval negative pi over 2 and pi over 2, and sine of y equals x, then sine inverse of x is y. And you'll see, you'll be able to see this when we do examples. For your cosine, it has to be between 0 and pi, and then for tan, it has to be between negative pi over 2 and pi over 2. Alrighty, so let's say we're given that sine of 5 pi over 12 is approximately 0.96593. We want to write a relation of its inverse. Well, in this instance, this is my x, right? And this is my y. So when I'm doing the inverse, I'm going to switch the points. So that means sine inverse of 0.96593 is equal to 5 pi over 12. Okay. Okay, now let's say we want to evaluate these different expressions. So here we have sine inverse of 1/2, and we want to figure out what is that going to be equal to. So firstly, we can say, well, let this be equal to x or something like this. So really what we're looking at is what value of x that when I take sine of it, I get 1/2. Right? Because again, we're going to be flipping the points. And so we need to figure out what value of x gives me sine, and sine, what value of x when I take the sine of it, or what angle when I take the sine of it, I get a positive 1/2. And we have to also note that this has to be, x needs to be between negative pi over 2 and pi over 2. Very important. So in other words, if I were to, let's say, draw my coordinate plane, this would be pi over 2. Here we'll have negative pi over 2. So your angle must be either in the first or the fourth quadrant. Okay, so if we think about it, we have two possibilities when sine is, for two angles, we have the sine of it being 1/2. And those two angles, I think I have the unit circle here as reference somewhere for us. So I can just pull it up so we can have it on the slide so we can kind of look at it for this problem here. Let me just kind of post it here. Okay, so if you look at the unit circle, sine is 1/2 at pi over 6, right? Pi over 6, and also sine is 1/2 at 5 pi over 6. But 5 pi over 6 is not where we need it to be. So that means that sine of pi over 6 is what is going to be equal to 1/2. So that means x, or you can just say x equals pi over 6, or you can just write the whole thing. Okay. All right, what about sine inverse of negative pi over 2? Very similar. This must be in the range of negative pi over 2 to pi over 2. So what value of x, so you can always rewrite it, so for what value of x, or what angle do we have sine of that angle being negative root 2 over 2? Okay, sine negative root 2 over 2. That's only this option here. And if we are going from, so recall that this must be pi over 2. If you look at it off that of that map, let's use this here, space. Up here would be pi over 2, and up down here would be negative pi over 2. So what this means is if I'm going down in this direction, I'm going counterclockwise, so I have a negative angle. So what angle would be here where 7 pi over 4 is? Well, that's going to be the 45-degree angle, right? Negative 45 to be more specific, which would be negative pi over 4. So x equals negative pi over 4. Or you could say sine inverse negative root 2 over 2 equals negative pi over 4. What about cosine inverse of negative root 3 over 2? All right, so again, you're looking for the value of x such that when you take cosine of it, you get negative root 3 over 2. But for x, we need to be between 0 and pi. So we need to be here, between 0 and pi. So only the top half of the unit circle. So what angle will it be? Let's see. Negative root 3 over 2. That looks like 5 pi over 6. So that means cosine of 5 pi over 6 equals negative root 3 over 2. Right? Or you could say cosine inverse of negative root 3 over 2 equals 5 pi over 6. Now, lastly, we are looking for, let me plug this in real quickly before it dies on me. There we go. So here we're looking for what value of x, or what angle x. So let's say x equals tan, or tan of x rather, equals 1. Now this is only possible, so if you recall, tan is sine over cosine. And so the only angles that will give us 1 or negative 1 is that 45 degree where the values are the same. So since it's positive, and for tan we're looking between negative pi over 2 and pi over 2, we have to be in the first quadrant. So this is going to be pi over 4. So we could say tan inverse of pi over of 1 over 4. And these are our answers. Okay. All right, so let's say we want to use, we want to solve this triangle here. Alrighty. So if you recall, if we're solving this triangle for theta, we need to figure out what trig ratio we can use to find theta, or what trig ratio would involve the two angles that are listed. So notice that the hypotenuse is given. The hypotenuse is given as 12, and one leg is given as 9, which is your adjacent. And the trig ratio that involves your adjacent and your hypotenuse is cosine. And cosine of theta is equal to what? Your adjacent, which is 9, over your hypotenuse. So 9 divided by 12. So if you are trying to find now what is theta, right? So we have cosine theta equals 9/12. If you want to find theta, we could utilize that property where we can take the inverse of both sides. So here, this would give me theta equals, and then you can plug this in your calculator. Your calculator should have a cosine inverse button. So you should be able to plug that into your calculator, and you would get theta is going to be roughly 0.7227. Okay, and so that's radians, but if we look at degrees, it would be 41.496 degrees. And one thing that you have to be careful when we're doing these problems is to make sure if your problem is asking for degrees, that your calculator is in degrees. If your problem is asking for radians, you want to make sure your calculator is in radians. What about this one? Let's say we want to find theta. So here now we have opposite and hypotenuse, which is sine. So sine of theta equals or opposite over our hypotenuse. So I could take the inverse, and that would give me what theta is. Once more, you can plug this in your calculator. I apparently didn't do this one ahead of time. So let me go ahead and plug it in my calculator while you guys are doing it. So sine inverse of 6 over 10, that's going to give me 36.8 as theta. Alrighty. All right. All right, so now we're going to, I'm just going to have this here for a reference for you all. It's better when we actually use them anyways. But we're going to do some evaluation where we find, like, say, sine inverse of cosine and stuff like that. But basically what I just said, this is appropriate, or this is the case. These values hold when we're between -1 and 1 for x for sine and cosine, and when we're, and all the time for tan. So that's kind of why these hold for the previous problems, because here we're between -1 and 1. Here 6 over 10 is also between -1 and 1. So that's why those values hold. All right, so now let's say we have this problem here. So we're trying to find sine inverse, right, of sine of pi over 3. So if you look at pi over 3, well, pi over 3 is 60 degrees, and it falls between that -pi over 2 and pi over 2. So that means that sine inverse of sine of pi over 3, well, that's going to be equal to just pi over 3. Right? Just because it falls in that -pi over 2, pi over 2 range. Now, 2 pi over 3, on the other hand, is not in that range, right? Because this is where 2 pi over 3 is on the unit circle, and that's outside of the range. So we can't just say, oh, this is equal to 2 pi over 3. However, sine of 2 pi over 3, sine is root 3 over 2. That's equal to sine of pi over 3. So we can just say, let me write that. So since okay. Yeah, so since sine of 2 pi over 3 is equal to sine of pi over 3, then that means sine inverse of sine of 2 pi over 3 is equal to pi. Alrighty. Okay, so for this problem, we have cosine inverse of cosine of 2 pi over 3. Now, 2 pi over 3 is in fact between 0 and pi. 2 pi over 3 is 120. So that means that this is just going to be equal to 2 pi over 3. So two pi over 3. All right, now let's see, negative pi over 3 is not between 0 and pi, right? So let's see, since cosine is an even function though, let's say cosine of negative pi over 3, we've talked about even functions. That's going to be equal to the same thing as cosine of pi over 3 because it's an even function. And so since it's an even function, they're equal. All right, and so because of this, and we know that pi over 3 is in fact between that 0 and pi, then that means cosine inverse of cosine of negative pi over 3, that's pi over 3. One way to look at this is you can let for B and D, you can let what's on the inside be equal to, let's say, x or theta or something like that. So you have sine inverse of x or rather theta. Never mind. I don't want to confuse you all. But hopefully you guys understood. If not, just post your questions and we can address them accordingly. Okay, so now let's say we want to evaluate sine inverse of cosine of 13 pi over 6. So notice that this is not on the unit circle, right? In the first rotation. It's not on the unit circle for the first rotation. We can actually split it in such a way that we can get it to be on the unit circle per se. So this takes a lot of practice though. So don't think, on the first hint you're going to get it. So 13 pi over 6 can be written as pi over 6 plus 2 pi. So I can write this as sine inverse of cosine of 13 pi over 6 is equal to sine inverse cosine of 13 pi, actually, no, we're going to plug this in, of pi over 6 plus 2 pi. And so at this point, notice that this angle is pi over 6 plus a complete revolution, because 2 pi is a complete revolution, right? And so so we can actually just look at cosine of pi over 6, right? And so we know that cosine of pi over 6 is going to be equal to root 3 over 2. So really we can evaluate sine inverse of root 3 over 2. So we think, what value on the unit circle, or what value on the unit circle, or what angle would give me a sine of root 3 over 2? Well, that's going to be pi over 6. Pi over 3. So recall how we usually do this. You would have sine of some value x equals root 3 over 2. So we're finding what angle, and the angle is pi over 3. What about this one? We want an exact value for sine inverse of cosine inverse of 4/5. Okay, so now in this problem, we can utilize our Pythagorean theorem and a right triangle. So in the inside, we have cosine inverse of 4 over 5, right? So that's what we're looking for. So that really means we're looking for the theta that gives me 4 over 5, right? I'm going to take cosine of it. Now, if I do a right triangle using the ratio that cosine is adjacent over hypotenuse, so let's say this is theta. My adjacent side will be here, which is the 4. So this is my adjacent over hypotenuse. So my hypotenuse would be 5. So since I'm looking for sine, though, I need my opposite. So I can use my Pythagorean theorem. And so we know that 4 squared, let's say this is a, plus a squared equals 5 squared. So 4 4 is 16 plus a squared equals 25. Subtract 16 from both sides, so a squared equals 9. Take the square root. And so we get that a is equal to plus or minus 3. Okay, so our triangle is going to be, we call it a 3 4 5 triangle. This is actually a common Pythagorean triplet. All right, so if we want to find now sine of theta, well, this is plus or minus 3, but we have to figure out if it's plus or minus. So we know that the theta that we're looking for, where the theta is equal to cosine of 4 over 5, cosine inverse. Let this be theta. Well, this has to be in quadrant 1 because cosine is positive in quadrant 1. That means that if we're in quadrant 1, then my sine, if I'm looking for a sine of this theta here, sine must also be positive. So if I'm looking for a sine, I'll take the positive value. So it's actually going to be positive 3 like I wrote before. So sine is going to be opposite over hypotenuse, which is 3/5. So my overall solution, sine of cosine inverse of 4/5 is going to be equal to sine of theta, because this has become our theta, right? Theta equals that. And sine of theta is 3/5. What about this problem here, where we want to find sine of tan inverse of 7/4? Well, we can do the same thing that we just did. Looking at the inside, we know that tan of theta equals 7/4. So if I were to draw my triangle, right? So we know that tan, if I put my theta here, tan is adjacent over hypotenuse. Over opposite. No, it's opposite over adjacent. And so now I need to figure out, what is my hypotenuse? So I have 4 squared plus 7 squared equals c squared. So that's 16 plus 49. Okay. If we work this out, this is 65 equals c. So this squared, take the square root. The square root of 65 equals c. If we were to find sine of this angle, so if we were to find sine of this angle here, or sine of theta, well, sine of theta is going to be opposite over hypotenuse, right? And sometimes we don't like to have roots in our denominator, so we rationalize. So this becomes 7 root 65 over 65. And that's your answer. So sine inverse of tan inverse 7/4 is equal to sine of theta. Actually, I'm sorry guys, this should not have an inverse here. This should just be sine. There we go. So it's not sine inverse that we're taking, it's sine. That's why I have this. So this is your theta on the inside. There we go. Yes, so this we're letting this be theta. And so sine of theta, we just found that. That's 7√65/65. All right, so we'll stop here for today. Be sure to look out for your homework. See you soon.